So I'm gonna go ahead and do some example problems. So some examples problems with pressure vessels and shrink fit. Uh, so we pretty much learned how to calculate stresses in a cylinder, a shell that has internal pressure applied and external pressures applied. And we learned how to do that for thick cylinders and also thin cylinders, both closed cap or they don't have any end caps. Okay. We also learned how you can use some of those equations too to figure out what is going on when you want to fit a bigger cylinder into a slightly smaller inner cylinder, and you basically have to shrink one of them and basically put that into the other cylinder. And I showed you how those calculations can be done. But for now, let me go and discuss the first example problem and how these equations can be used. So one of the things I like doing personally when I solve a problem, I like to write down all the numbers are given to me and try to understand what the problem statement is telling me. That's what I like doing, and I think it helps quite a bit. So it says here I have a thick wall cylinder. Well, I don't start drawing stuff right away. I like to read the problem statement at once. So it says a thick cylinder with a 0.3 meter and 0.4 meter internal and external diameter is fabricated of a material whose ultimate strength is 250 megapascals with a Poisson ratio of 0.3. Okay, that's good enough for me. I think I can now draw something that makes sense to me. It's a thick cylinder. It's clearly not perfect because I don't have the pen, but good enough for me now. And it's saying here that it gives me the dimensions. I can put it here if I want. So I have this radius here. That radius is 0.15. And this radius here is 0.2. So I'm kind of making a quick sketch. And it's giving me the strength and the Poisson ratio. It's asking me if the internal pressure is, if the external pressure is 0. So this pressure outside here, P naught, is 0. And the pressure, and then it wants me to determine what the internal pressure is inside of the cylinder. It wants me to figure that out. So that's the first problem that's being asked. So why don't I just jump to that first case? What pressure should be inside if the ultimate strength is 250? So this is what I like doing. I like to create variables and kind of write everything out. So given this information, find this stuff. So in this case, they're asking us to find the pressure inside the vessel so that the ultimate strength is not exceeded, 250 megapascals. So first, what I want to do for the case A, which is the one I'm looking at, is what radial location gives you the maximum stress? That's the first question I want to ask. Because I don't know where in the cylinder the thing is going to fail. I don't know where it's going to fail. So I have to figure that out. I know the external pressure is 0 for case A. For case A, which is the first question that I've been asked, P naught is 0. Do I know A, the inner radius? Do I know B, the outer radius? I'm pretty much golden because I have everything except for one thing. I don't know PI. That's fine. We can figure that out. For hoop stress, I also have the same situation. P naught is 0, P naught is 0. Now, for when I design something, don't I want to design it so it doesn't fail at the max? I wanted to make sure that the failure occurs at the maximum stress, obviously. That's where it's going to fail first. So if I want to design something, I have to design based on that. So I need to figure out at what radius that happens. At what radius is this maximum stress occurring? So what I did, I looked at the stress here on this edge and then on this edge, right? So maybe the stress is higher in between, but it's unlikely. So I just checked those two cases. So for case A, when you substitute everything I talked about with the P naught being equal to 0, everything simplifies nicely to this equation. So we can now check at R equals A, the radius at A, and see what happens. When I plug in A there, and I did it right here, if I put radius of A there, this whole thing simplifies to pi, which makes total sense. We talked about that. The sigma radius should be, this radial stress should be equals to pi, the pressure inside. We discussed that earlier. Sigma theta, though, the hoop stress is pi b squared plus a squared, b squared minus a squared. Now let's look at the radius, the stresses at the r equals b. At r equals b, the radial stress is 0. The hoop stress, however, when you do all these calculations, gives you 2a squared pi divided by b squared minus a squared. And so in reality, clearly the radial stress is not the one driving the problem. That's 0 and that's pi. The only thing really that's the highest is either this one or this one. But you can see that pi shows up here and pi shows up here. In the denominator, you have b squared minus a squared. And for this particular problem, if you compare b squared plus a squared and compare that to 2a squared, you will find that this will be greater. So therefore, that's where I'm going to base my design off. So that's the most critical case, this one here. The critical stress is what I meant. So then what I'll do is say, okay, well, this is going to be then equal to the strength of the material. Guess what? I know B, right? I know A, and I know the strength. The problem statement gives it to me. So all I have to do is solve for the pressure. So Pi equals S times this. The strength is 250 megapascals. B is known. A is known. Plug it in all, and you get the pressure, internal pressure 70 megapascals. Now, in real life, you don't design something so it feels right at the strength of the material. You apply a factor of safety. So typically for fuselages, for aircraft, for example, you'll take that 70 and you'll divide it by 1.5, say, a factor of safety. And so you'll never go above that pressure, because if you go above that pressure, then you're going to step into a problem with the design. Is this making sense to you or not? The next question is case B. Case B says that the pressure inside is 0, but the external pressure is P naught, to find that pressure external. The previous question was, what is the internal pressure if the external pressure is 0? But this question is, what is the external pressure if the internal pressure is 0? So that's easy. All the PIs go away, 0, 0, 0. And I want to figure out where the worst case is. So when you do all the calculations, these are the stresses you get. Obviously, PI is not showing up. Let's check at R equals A now to see where the stress is highest. Is it here at R equals A, or is it R equals B? Where is it the highest? So I'm going to check R equals A first. And when I do that, sigma R is 0, makes sense. There's no pressure internally at R equals A. So sigma R should be 0 because that's the radial stress, which is exactly where the tractions are being applied, and there's no tractions, that's 0. So that's making sense. Sigma theta, however, can be found now, and sigma theta is a hoop stress. I'll plug in R equals A, and I get this equation here. At R equals B, then I'll check it. I get 0 for that. That I'm not sure if it's 0, actually. There is an error here. I think this should have been P sub I, or there's probably an error because this radial stress in the outer radius should be equal to the outside pressure. So this is an error. Okay, don't pay attention to that. I apologize for that, but perhaps you can fix it for me. Find my error. Sigma theta R equals B. I can also find that. And if I compare this to that one, you find out that this is the most critical case, the one here. I will not do it now, but this is what you find out when you actually do it for this particular problem. So when I do that, I can now set this the strength of the material. Now, typically the strength in compression is higher than the strength in tension. Obviously, this whole thing is in compression. But in this case, they give you a single value of 250. So just use that. So that's 250. The strength is this. And then you plug in all these numbers in and you get the pressure of 54.7. So you can see the pressure that fills the cylinder is lower in external pressure than internal pressure. which is quite interesting. This error here should be corrected. I hope you can find it. All you have to do is plug in R equals B here to get the correct equation here. So again, I apologize for that, but we can fix it now. The next question is, what is the deflection at R equals A for the very first case? Case A was with internal pressure. I know the internal pressure already because I designed it. So all I have to do is the internal pressure is known because I found it. It was 70 megapascals. If you recall, that was this pressure here. 70 megapascal for case A. But the external pressure for that case was 0. So all you have to do is use the radial equation for deflection. And this question, what this question is asking, if you're not sure what I mean, is asking you how much this radii grows, like how much this point moves outwards when you pressurize it. That's the question. Try to understand the question from the physical point of view. Otherwise, you're going to be just using equations with no real understanding. So this is a very easy equation because I know Poisson ratio, I know the modulus of the material, I know the radius of the material, the radius of the cylinder, I know PI because I calculate 70. P naught is the outside pressure, the 0. Quick equation, plug it all in, and it's just easy calculation. I'm not going to go through it because it's just plug and play. But you can also find the radius, the deflection R equals B too. All you have to do is plug in for R, put B there, and for R, put B there. Make sense so far? Let's go to the next example. Now, this is a very interesting example. It's a pressure of a cylinder with rigid boundary. So what this is asking for, let me explain it well. So I have this cylinder. It has a pressure outside that's been applied, but internally I put a rigid cylinder so that that cylinder is kind of constrained in the inner cylinder. I give you the radius of 100, the external pressure of 3000 pascals. I also give the modulus and Poisson ratio. The question being asked is to calculate the stresses and deflection throughout the whole thing. I said at R equals 2A, but you should be able to get it for the whole thing. Why not? I had the formulas. So I start with the very equation I had before. The radial deflection is given by this, right? I know the radial deflection. I also know the following. I know that this whole thing, this radial deflection, has to be 0 at R equals A. You agree? If I have a rigid constraint there that does not allow it to move, then isn't the radial deflection there 0? It has to be. So I take this equation, set that equal to 0. And obviously, when I do that, there will be an internal pressure that gets developed to that cylinder because I don't know how much it is, but there is something going on there. Now, do I know all the dimensions? Yes, I know what A, I know the radial, the A and the 2A. I know all these numbers. So all these things are known. So I can plug it in. I can put Ri as A. I can put R naught as 2A. In this problem statement, they said that the radius, the outside radius was 2A. So you can plug in all these numbers straightforward. And all you have to do now is solve for PI relative to PO. Remember, you know PO. We're trying to find the internal pressure that prevents the inner radii of that cylinder to move. That's what we are after. So there you go. I tried to solve it little by little, and I did this in the airplane as I was coming down here, which is the reason why you don't have this charts. But here you can see, I tried to solve for PI in terms of P naught. I multiply everything out. It's kind of painful. Modulus cancels out, the 3 cancels out. So I just kind of multiplied patiently until finally there's turbulence, and it came out very nicely. The pressure that prevents the inner radii from moving because there's a rigid constraint can be found. If I know P naught, I can get you PI, which is cool. Because did I plug in what A is? I didn't even plug in what A is. But I can tell you that the pressure is this much, then PI needs to be this much so that this inner radii does not move because it's a rigid constraint. I don't know. I find that very cool that the A did not come into play, that I can calculate internal pressure that makes this happen. Now that I solve PI in terms of P naught, I'm pretty much done. Now I can just plug in, use the general formula for U, the deflection as a terms of radial deflection. I can just use that equation. I know PI in terms of P naught already because P naught is given to you. So I know PI. So all I have to do is just plug in what PI is and P naught is. I know the radius, the internal radius is A, the outside radius 2A. Just plug it in, and that gives you the radial deflection at any point through the thickness. I can then find the stresses the same way. So stress is straightforward. I know PI in terms of P naught. I can calculate, and I know A, and I know B is 2A. I can just plug that in, and I'm able to find the pressure, the stresses through the thickness of that ring. Yeah, so I did it here. I tried to do it here, but we won't go through that. We'll just move to the next example. You know, I just hear what I did. I tried to calculate what the hoop stress was at R equals A out of curiosity. When you're boarding an airplane, that's what you will do. So I say, okay, what is this hoop stress, right? I was just kind of curious if the hoop stress here, I was wondering the hoop stress here is 0 because it's not moving, right? But it turns out it's not exactly 0, but it's close to 0. So I'll invite you to do it. I'm going to flash it here. So when you see it in the video, you can try it. What if I did that? So I'm going to flash it here. I did it here. I tried to do it myself. Right? Because I know PI in terms of P naught. So I just plugged in one versus the other. And when you do that and you choose, if you choose a Poisson ratio of 0, you get this hoop stress is 0. If you don't get a non-zero value. You get something. I was just kind of curious to see what will happen. Check it out at home. See what you find. See if you got the same thing I got. Another example. Why not? The more examples, the more we learn. Okay, so what about this case? This is a very interesting case. What about if I have an infinite plate with a circle, so I have this body material with open hole, with an inside pressure P, and I want to know what the stresses are near the hole or even away from the hole. So what I do, I use the same formulas I had before. So obviously there's no P naught. You agree? There's no P naught, no outside pressure. So the formula's reduced to this. Very easy looking. I can write this differently though. So I wrote it so that I divided the denominator by B squared. So when you do that, you can rewrite these equations so they look like this. Okay. So I just took the same equation, but wrote them differently. Okay. All I did again, I extracted B squared out of that so that you get 1 minus A squared divided by B squared. But because I extracted B squared out of that, I had to multiply with this right-hand side here. So I get 1 over B squared minus, and the B squared cancels out. I get 1 over R squared. So this equation here is the same equation as this one. I just wrote it differently. Agree? It's the same thing. I took the same equation here, which is here. I just extracted B squared out of it. So I get 1 minus A over B squared. And when I extract B squared, you can then get 1 over B squared plus 1 over R squared. And you get that, this expression. Now, do you agree that the radius in this case is infinite? Like B is infinite? The outside radius is infinite because it's infinite plate, no? You agree with that? So if you agree with that, don't you agree that if B is pretty much infinite, because this radius here goes to infinity, I mean, this body of material keeps going forever, don't you agree that 1 over B squared is pretty much 0? So this is 0, that's 0. Do you agree that A is much smaller than B? So A over B squared is pretty much 0? So I did that. That's what I did. And when you do that, everything simplifies to this expression. I can tell you what the stress is radially, sigma RR. I can also tell you what it is tangentially. Make sense so far? And that stress dies out. You can see here by the R squared, 1 over R squared. So the farther I go, do you agree that this, as R goes to infinity, that stress goes to 0? So that makes sense. If I apply pressure to this hole, that pressure is going to die out as you go out there to infinity. I plotted that pressure, that stress, so you can see what happens. I did it dimensionally, but you can see how it's dropping to 0 as you move away from the hole. Both the stress states are given here. That's the sigma r and that's sigma theta. And you can see how that's dying out as you go away. So with that, I want to thank you for attending this lecture.